Okay, we are recording now. Um, I hope you've watched the lecture from last class. Today's goal is to kind of put everything we discussed last class into context, kind of revisit a little bit. And that would be an opportunity for you to ask any questions, lingering questions that you have. And then once we have covered today's a little bit on localization, like we started last class, then we are going to get into beamforming and talk a little bit about the foundations of beamforming and angle of arrival. And then next class, we are again going to look at applications of beamforming and angle of arrival in localization. Okay, so that's basically the plan. Any questions thus far? Guys, I'm assuming you can hear me, correct? Thanks. Utkarsh, have fun. Anthony, thanks for turning on your videos. If others can, much appreciated. Okay, let's get started. So last class, we talked about essentially two things. One is this Wi-Fi based indoor localization, where we essentially made the point that GPS signals do not penetrate indoor environments, and Wi-Fi is kind of a proxy for satellites. And if you can use Wi-Fi signals for localization, that might enable indoor localization, right? And we talked about how there are some certain differences at a very high level, certain differences between GPS and Wi-Fi. And we quickly got into this one idea from 1999, which essentially said that, look, we can measure the power of the Wi-Fi signal, which is called a received signal strength, RSSI, and kind of fingerprint on that power, right? Fingerprint meaning like every location has a different power, hopefully. And if I can somehow create a database of the location to power mapping, then later when someone new comes to this building, that person's power measurement we could take and somehow map it to a location and hope that that location is reasonably good. So this was a kind of a simple idea, but 20 years back now, if you think of these things, when Wi-Fi was not even there, someone thinking of these kind of things, we should definitely appreciate however simple the idea is. And we talked about KNN classification using this. And then we also talked about convolution, where we said, look, in reality, the reason why Wi-Fi radar didn't work that great, like the accuracy was somewhere between 5 meters, 10 meters, and there's a long tail in that distribution, is that the power is not like a simple line of sight power. It's like multiple paths adding up, right? And because the multiple powers add up in very random ways, depending on what the delays are for these echoes, right? The signals would add up in random ways. Sometimes it can constructively add up. Sometimes it can destructively add up. And as a result, the power that you receive at a given location can be very different. Right? And then we started talking about how do we even think about this kind of impact that the room is having on the signal, on the received signal. And that led us to this notion of somewhat formalizing this notion of what a channel means or what this room's impact means. And we talked about multipath and we talked about the core notion of convolution. And we said, look, we can separate the channel out, which is essentially a vector, H, but that gets convolved with X, X being the source signal, like we talked about X0, X1, X2. And what you receive at the receiver is essentially this convolution of HX, HN with XN, added with some noise which comes from the receiver's hardware. Because remember, this HN convolved with XN is what impinges at your antenna, because that is that line of sight path added with all the echoes or all the multipaths. but your antenna is now receiving this voltage and then sampling it. And the reception of that voltage is not going to be exactly the amount that is impinging on the antenna. There are variations there. And also the sampling is not going to be the exact voltage that has come. There are sampling quantization kind of errors. And all of that put together, we are going to say, oh, there is some error that gets added in your received signal. Right? And then we talked about, okay, look, how do I estimate the channel? Well, I know all these packets that are sent by Wi-Fi, 5G, whatever, all these wireless technologies. If you do not know X and you do not know H, there is no way. If you do not know X, there is no way you can detect H, because then both H and X would be unknowns, right? So that is like saying, I give you 10 and I say, you know what, 10 is the multiplication of two numbers or the convolution of two numbers. Tell me what those two numbers are. There's no way you can say H and you can decode both H and X. So what wireless technologies do is that at the beginning of each packet, they insert a known set of bits, which are called a preamble, or also often called a pilot sequence. And this pilot sequence essentially means that the receiver knows, look, the first few bits are definitely going to be known. So which means this XN is known for the first, let's say 1000 bits, or maybe 500 bits. And now that you know this, you can estimate H. And we said, how do you do that? This is not multiplication, this is convolution. And here is a property that I just gave it to you, and just take it from me, is convolution in time is multiplication in frequency, and the vice versa. Convolution in frequency is multiplication in time. And you can prove that. This is not a difficult proof at all. If you start with xn times e to the power minus j 2 pi by n mn, if you start with that and you do convolution, you will be able to prove it. It's not very easy, but it's not too difficult. And if you now think of, and this property is very, very useful, because whenever we want to do things with convolution, we'll say, hey, I'm not going to get into that mess. I'm going to move to frequency domain, right? So H convolved with X becomes H times H of F times X of F. I'm going to do everything in that domain, because there I know AX equals B kind of techniques, right? This is kind of AX equals B kind of technique. Again, see that this is AX equals B. This is B, this is AX, right? You have to write the channel in a way that it looks like a matrix, not hard. And then once we figure out everything over there in the frequency domain, we'll just do an IFFT and get back to the time domain. Okay. So once I get HF, I go back to the time domain with an IFFT. There's an IFFT here, and that's where my H is. And for the rest of the packet, where I do not know the X, I know the H. So I'm going to use that H to decode the rest of the X, right? What is the assumption that we are making when we are decoding the rest of the packet with the H that we estimated from the first part of the packet? Is there any assumption that you can think of? When can it not work?
When H is changing as you move.
And H is changing as you move, right? You are driving in a car and you're talking to your friend from a cell tower. Right? The cell tower signal is coming to your phone. And for every packet, you're talking on WhatsApp, let's say. So it's like internet. Every packet has that pilot sequence. Now, if you're moving, the channel is changing. These reflections are changing constantly, right? So if your channel is constantly changing, when you estimate your H from the pilot sequence, and you use that for the rest of the packet, when the rest of the packet is coming in, maybe there is a tree in between the tower and your car, and the channel is completely different, because the leaves of the tree makes the multipath echoes become very random. And as a result, the decoding is not going to be successful. Okay. This is oftentimes at a high level there's some notion called the coherence time of a channel, which means how long should I assume that the channel is stable? Meaning if I estimate the channel here at the beginning of that coherence time, the channel is still reasonably the same at the end of the coherence time. Okay, so this is called the coherence time of the channel, and typically packet sizes, the length for which a packet should last, is designed to be less than the coherence time of the channel. Right? Otherwise, the problem is difficult. Right? So when a rocket is going up for launching and they're communicating to ground station at Houston, the coherence time of the channel is much smaller. You agree? Why? Because that rocket is very fast, right? So whatever channel you estimate now, in the next time instant, the channel is changing. So there, the packet sizes need to be smaller. But for a slow walking person jogging, the coherence time is larger. Right? So again, these things go into wireless communications. We do not have too much time to look into it. But this should give you a reasonable idea of what is really the core engine behind estimating the channel and using that channel for localization. Any questions thus far? No questions mean two things. Either you're totally clear or you're totally at a loss. Tell me. Okay. I'm assuming it's the former. You're totally clear. If that is true, let's finish up the first round of discussion on localization with the following. Okay, good. So we said that we have a Wi-Fi access point. Let's again step back from starting from GPS. And we said, look, we have a Wi-Fi access point. And if you want to do GPS-like techniques, we essentially want to measure this distance R, which is the range from the Wi-Fi access point to my mobile phone. Right? So the real question was, how do we measure this range R? Now, one possibility is time of flight, or often called TOF. This is what GPS does. Right? GPS does time of flight. You agree? Right? At least the basic GPS does time of flight. Right? You know how long it took for the signal to come from the transmitter to the receiver. But time of flight is kind of hard without time synchronization. And that is why we put so much of effort in doing time synchronization across the satellites in GPS and also between the user and the GPS satellite. And also, time synchronization in Wi-Fi is difficult because you do not know the Wi-Fi AP's location. Remember our discussion? You cannot ask your neighbor, can you please put your Wi-Fi AP exactly at coordinate XYZ? Right? So time of flight based approaches in Wi-Fi is impractical, is difficult, right? For practical issues, right? So the other possibility is, can we do something from the power of the line of sight signal? Right? So let's unpack this line of sight signal a little bit. Let's understand it. Understand this. So when a Wi-Fi antenna or any antenna transmits, typically these antennas are what are called omnidirectional antennas. What does that mean? It means that this antenna over here that is connected, let's say, to a Wi-Fi access point. This is your Wi-Fi access point. When the antenna radiates the signal or sends the signal, the radiation kind of goes out like a sphere in all directions almost equally. Ideally, it goes out equally. Okay? This is called omnidirectional. Omni means all, and direction means direction. So it's all directions, the power goes out, the signal goes out. Right? So received power at any distance R decays as 1 by R square. Why? Can someone tell me why? The power that you get along any direction at this distance r, at this location, which is at a distance r, or at this location, which is also at a distance r, at this location, the power decays by 1 by r square. Tell me why. Why r square? Okay.
Is it because if you consider the power to be surface area, then the surface area increases by r squared? That means you have less power covering the same amount of...
Very good. Why should I consider power to be the surface area? You're almost there. Why is the power surface area? You're there. Every pixel on that surface of the sphere of radius r has dash power. How can you fill it up? Every pixel on that sphere, okay, let me say this again. For an omnidirectional antenna, every pixel on the sphere r would experience dash power, equal power. You agree? Right? So every pixel on that sphere will experience equal power because the signal is radiating out like a sphere, and it's radiating equally on all directions. So if you stand on any point on that sphere, you are going to get the same power as any other point on that same sphere of radius r, right? So let's write that. Because surface of sphere around the antenna is 4 pi r square. That's the surface of a sphere. Okay. And every pixel on the sphere should have equal received power, since this is omnidirectional antenna. Right? So if you think of the received power as PR and the transmit power as PT, at a distance r, how much power do you expect? It's PT, that power that was transmitted, or that energy that was transmitted. At every point on the sphere, it should get amortized, or it should get scattered, distributed equally. So that should be that power divided by 4 pi r square. Right? Now, of course, there is absorption. Maxwell had very precise formulations. There's absorption in the medium and all of that. We are engineering people who would not get into that much of precise details of exactly how the wave propagates. We are going to summarize all of that into some k over here, where k is some constant. Okay. So this is the received power. At range r, which is the transmitted power divided by k times 4 pi r square. 4 pi k, they're all constant. So all you need to know is this is a function of r square. So as r increases, the power drops non-linearly. Very good.
Professor, I had a question.
Yes.
Just as a quick side note, could you just at least say what the equation is called?
Which equation?
The one that Maxwell or whatever did.
Oh, I think it's called Fritz's equation.
Okay, cool. Thank you.
I think. Don't quote me on that. Okay, good. So one thing to note is, if the power is going to degrade by r square, and suppose you know the transmit power, can you tell me something about how we can use this for localization? Suppose you know the transmit power with which your Wi-Fi AP at your home is transmitting. And suppose you live in some magic world where there is no multipath. Or let's say you are living in space and there's a Wi-Fi AP that is transmitting and you have your phone and the phone receives power. There's no multipath in space, in deep space, right? There's no reflecting surfaces. Can you say your location from that received power, from this received power?
You make a mapping from the power to distance, and once you have like 3 distances, you can do trilateration.
Perfect. Right? If you have a map, you can map your received power to distance because you can solve for R. And if you have 3 spheres, right, you can solve for your location, same way we did for GPS. Okay, so that's possible, right? But unfortunately, you don't live in space yet, right? We still have some time to colonize Mars. And even if we colonize Mars, humans will put up reflection surfaces, and again, multipath will come in. So line of sight power-based localization is more of a utopia. That doesn't work. So what happens in real world is that with multipath and echo, PR becomes, this power, received power becomes more complicated, right? And this is something we already talked about. Now, when you have this Wi-Fi antenna radiating omnidirectionally, and even though the receiver is over here, let's draw that. This is your phone's antenna in red. The line of sight path power, the LOS power, comes to you directly, no problem. You're very happy about that. And that follows the PT by 4 pi r square equation. But then from your ceiling comes another signal. There's a furniture on your floor that reflects, then it reflects on another object, reflects on another object, and it comes. Many such paths. It reflects on your body and goes to your mobile phone. It reflects on your laptop. It reflects on all kinds of places. And as a result of that, what your mobile phone or your laptop is getting is the following. It gets this line of sight path. I'm just drawing a simple sine wave, right? In reality, the signal that the transmitter is sending has many frequencies, but I'm just drawing a simple 1 frequency sine wave, right? So this is the line of sight path that arrives at your receiver. But after a while, after some delay, which depends on how far the ceiling is, the next path arrives. And after some more delay, another random delay, another weaker path arrives, another weaker path arrives, and so on. Agreed? And all of these are adding up. At any given instant of time, at this time instant, all of those echoes, line of sight plus echoes, are adding up. So delays copies add up, and now tell me what is the power of the received equation. Can you say anything? It's very hard. It's random. You have no nice, clean analytical equation of what the received power is in terms of the transmitted power. Okay. So in this kind of a scenario, people have done empirical measurements over various kinds of environments and has seen that, look, the received power still shows some relationship to distance, right? But if you really plot the received power PR with distance, I'm plotting it at this corner, you will see that the power relation looks like this. Does that make sense? Right? Because remember, your received power is still dominated by the line of sight power, right? If you're close by, your line of sight power will be strong, right? It'll get, sometimes it can be bad, but most of the times it will be strong. But as you get further away, the line of sight is weak and the reflected power is weak. Right? Guys, I want you to make one more concept very clear. Suppose, okay, I'll come back to that later. Forget it right now. Forget it right now. Okay. So when you look at a graph like this, some people have said, look, it's not that this is completely random. What if we run some regression and we fit some line? Right? This is fitting. Polynomial. And if you fit that polynomial, then you can get something like a Fritz's equation, and you can say, look, PR is PT divided by K times 4 pi, but now instead of R square, you have some R to the power alpha. So what you fitted over here is that alpha. You fitted an R to the power alpha curve, and you say, what alpha fits it best? Does that make sense? And this alpha is called path loss index. And this often shows up in a lot of articles and things you'll read. Path loss index. And measurements, empirically, people have seen, of course, hey, what is the lower bound on alpha? Alpha has to be greater than some value. What is that value?
Is that 2?
That is 2. Right? And alpha is typically less than 4. Make sense?
Even in like highly reflective
Adil, go ahead. Adil, go ahead.
Even in like highly reflective areas, it's like less than 4, or
Highly reflective areas?
yeah, like if you have a lot of like metal equipment.
Yeah. A lot of metal equipments. We are going to go into that right away. Hey, but actually I made a mistake. Utkarsh, I made a mistake when I said 2 as the lower bound. Can you think of a case where you can get more than 2? Sorry, where you can make it less than 2. Means I am not going to, sorry, let me just back up over here. This thing that I wrote over here is empirical, meaning this is what is typically measured. But suppose I tell you, is it ever possible to make alpha less than 2?
Oh, is why you're saying this because I brought up the path loss stuff? Like, say you had a lot of constructive interference.
Exactly. Exactly. If I could place my reflectors in a way that all the signals that are going in all random directions, all other directions, I place reflectors in a way so that like a lens, the reflectors reflect the signal so that they all add up constructively at the receiver. Then I have no loss. Every power or every energy that is being radiated from the antenna, I could lens it, I could beamform it. I could make them add up by reflecting at the receiver. Agree? So the only loss I would have is any surface when it reflects, there's some absorption at the surface. Okay, so that's the only loss I will have. But if you can create this reflective surface, which has very little loss, but all the energy that is going towards in all other directions other than my receiver, I somehow make them reflect towards my receiver, and I make sure I reflect it in intelligently so that all the delays add up constructively, right? So I make all these delayed paths move. I move this, I move this, I move this, I move all of them so that they add up constructively. I'm not losing any power at all. I'm getting all my transmitted power to my receiver, except for the reflection absorption, the absorption at the reflecting surfaces, and if there are some absorptions in the medium. For acoustics, there are absorptions in the medium. By the way, guys, all these that we're talking about is true for acoustics as well, acoustic signals as well. Right? So nothing changes. Very good. So, but empirically, it's hard to get below 2, it's hard to get above 4. Okay. So deep space, it's 2. This you agree? Right? In deep space, there is no reflector, so you cannot get any gain, but you don't have any losses either. So it's going to be exactly a sphere. So in deep space, alpha is 2. In a soccer stadium, alpha might be 2.75. I'm just making things up. These are just made up examples. In an apartment room, alpha might be 3.1. Right? It's getting worse. Right? At least in a soccer stadium, there are not that many reflectors. So you have the line of sight dominating. In a room where there are many other reflections coming in, it's a problem. In an elevator, it can swing either way. Right? You can get super lucky and all the signals bounce around. Nothing is escaping. Every signal is bouncing around. And in some location in the elevator, it is possible, although with a vanishing probability, that everything constructively adds up and you get less than 2. But typically people see that the attenuation is more. Because every reflection with real surfaces, every new reflection is absorbing some of the energy. So your attenuation becomes small, your signal power becomes small. The important point to take away is that alpha will vary from one location to another. Right? And that is essentially the core motivation for radar. Right? Radar is essentially saying, look, when I fingerprint RSSI, I'm actually fingerprinting alpha. Right? And that part I hope you are clear on now. The only thing is that it's very hard, because now if in a shopping mall, if other people are moving, reflections would change, alpha would change, RSSI would change. Whatever you trained on is no longer true. Right? And that is the reason, the fundamental reason why you cannot get precise accuracy. Your accuracy swings between 5-10 meters to even pretty large values. Questions? Okay. But you know what? Can't I, from the signal that I've received, if I could somehow pull out the power of the LOS, then I have some opportunity, no? All of this problem is happening because the line of sight power, which has a very clean R-square relationship with the transmitter, that line of sight power is getting polluted by all the multipath. If in all this mixture of line of sight and multipath, I could somehow eliminate the multipath and only have the line of sight power, I have some hope of localization, because then I would know that I am on a circle around the transmitter. I don't know where on the circle, because at all points on that circle, the line of sight power will be the same. Are you with me? Right? But still I have a circle, and if I know that circle around a Wi-Fi AP, and of course I need to know the Wi-Fi AP's location, which is a problem. But if I knew the Wi-Fi AP's location, let's say in a shopping mall, the mall owner is deploying the Wi-Fi access points, and he or she could very well say, hey, deploy these Wi-Fi access points at these precise locations. And once you know the locations and you know the circle, you can do trilateration. How do you know? Can you pull out the line of sight power? Right? That's the question. And for that, we started, now we can say, look, we can model this signal, received signal Y, as nothing but the line of sight signal X plus X that's coming over echo 1 plus X that's coming over echo 2 plus so on, many, many echoes, right? Essentially, the received signal is the line of sight signal plus delayed copies, right? These delayed copies of the line of sight signal. So basically all these are, let's write it, delayed copies of the line of sight signal. And last class we said, look, how are these delayed copies coming in? This is because the room is essentially behaving like your enemy who is delaying these copies, right, by these reflectors and adding them up at the receiver. And then we said that the room is essentially like a channel, and the received signal is nothing but the convolution of the channel and the signal that the source is sending, which is X. And that we wrote as H convolved with X. This H, okay, this H is nothing but a vector, by the way. I hope you remember that, H0, H1, all the way HL. It's a vector. And I also hope you remember that if you think about H, let's just do it over here. H is also actually like a signal. I mean, any vector is a signal, right? So H often looks like this. What does that mean? This is what H looks like. What does that mean? This is which path? Anyone? This is time. This is H. Which path is this?
Line of sight?
Line of sight, exactly. This is the line of sight path. And this is the power of the line of sight path, the Y value. Right? After some time, delta 1, this is the first multipath, or echo 1, echo number 1. Right? Then after some longer time, maybe the first multipath, maybe your device is close to the floor, so the first multipath comes quickly. And maybe the next multipath comes from the ceiling, but because the ceiling is higher, maybe you're in a shopping mall, the ceiling is higher, the next multipath comes after a little bit longer, delta 2 is larger, and that is your second multipath. Right? And these multipaths keep coming. Can anyone say any properties about this multipath signal? Sorry, this H signal. What can you say anything about this H signal? For instance, can you say anything about what the shape of these values should be? Can they be random? Can they be random like this? Or should they be monotonically decreasing? What can you say about the shape of the path, of the channel? This whole thing, these things are called channel impulse responses. We talked about this last class. So tell me, what can you say about the shape, this shape of the channel? Anything? John says this should be decreasing with time due to attenuation, right? Very good. Every reflection that is coming later should be reflecting, it should be attenuated. But can you tell me one scenario where the first value of the channel is less, but the later value is larger? By the way, these are called channel taps. So these are called channel taps. Every value where there's a non-zero value, that's called a channel tap. So can you tell me when first channel tap, which is the line of sight path, has less value than second tap? Can you think of a case?
Let's say the line of path have to go through a wall, but the reflection actually like just about to evade that wall.
Perfect. Right? The signal, the line of sight has to go through a wall. So this is your transmitter. This is your receiver. There's a wall over here, but there's another wall over here. So line of sight goes through a wall, but the reflection does not. Yes, those pesky walls. Okay, that makes your line of sight. So you really cannot, in general, it is true that roughly it should have this decreasing shape, but it may not be always the case. That depends on whether these signals are passing through walls. Very good. So this H is your channel, and often this H is called the channel impulse response. Oops, 1 second. That's how I spell response. Shoot. Or CIR. Or often called, so I'm just giving you these names so that you never get confused when you read papers or you read other articles, or also called room impulse response, or RIR. Right? Essentially, what is the room or the channel doing to your signal? And of course, the point is CIR or RIR is a function of the TX and RX. TX and RX is transmitter and receiver locations. Right? It's a function of both the transmitter and receiver location pair. If you move the transmitter's location, channel impulse response will change. If you change the receiver's location, channel impulse response will change, right? In any case, any movement channel impulse. By the way, guys, if the transmitter and receiver are fixed, can I say that the channel impulse response will remain the same in real environments? You're in a shopping mall. The transmitter Wi-Fi AP is fixed. You're standing at a location with your phone and you're holding your phone steady, fixed. Will the channel impulse response be over time will remain the same? Answer.
I think there should be some noise that's going on because of people moving and just
exactly. Channel impulse response can definitely change because other people would act as reflectors. People are reflectors very much. Okay? So as people move around, the reflectors would change. So definitely channel impulse response would change. In fact, it's interesting. People are good reflectors and people are also good attenuators. So signals do not go very well through human bodies. And that is partly because human bodies contain a lot of water. Okay? And the frequencies that Wi-Fi uses are actually resonant frequencies for water. So when the signal travels through your tummy, and if you've drunk a lot of water or other drinks, the molecules resonate in the same kind of frequencies as the Wi-Fi signal, and the signal's energy gets absorbed. Okay? But reflections happen much better. Okay? Just a side trivia. Great. Okay, so now that we know that the RIR and CIR, and we can estimate the RIR and CIR, right? I mean, they're the same thing. We can estimate the channel. Imagine we know the, does that mean, I'm reading a chat. Does that mean water now contains calories? I'm not sure. I don't know how that goes, Utkarsh. Actually, now that you make me think, I mean, the water will be heated slightly if it absorbs energy. It will. Yeah, let's talk about that at some point, a new way to burn fat. Yeah. You've heard about all this talk. Okay, let's chat for a little bit. You've heard about all this chat about 5G, right? Here is another random thought. So 5G signals are at a much different frequency, okay, especially the high frequency ones, okay? And it turns out that these high frequency 5G signals get absorbed by oxygen heavily, okay? And it seems, again, I do not know these things very well, but I've heard these things peripherally. It seems that oxygen molecules actually can undergo changes because these 5G high frequency signals are passing, and the oxygen is kind of absorbing the energy from these signals. So one of the thoughts I think we discussed at some point is, if there is a fire, like say wild forest fire, it's hard for any kind of water sprinkling or sand sprinkling or any kind of sprinkling to stop, right? Should we just blast that area with 5G signals? and if you can do it, right? If the oxygen content can be blocked, or because of that 5G signal, does it have any effect in cooling down the fire? Okay, so there's these random crazy ideas, but who knows? This is it's age of SpaceX. And in fact, another idea another idea which is not so crazy is, if there is water in the air, then 5G signals and Wi-Fi signals would travel differently. So can we predict microclimate, let's say in a farmland, by understanding the received signals from a receiver, where the signal is basically propagating over the farm, and you have a receiver at the end of the farm, and by receiving that signal, can you estimate moisture content in the air? Right? And if you estimate moisture content for all kinds of precision agriculture and digital agriculture, which are very exciting topics now, because now you can take a drone and you can put fertilizers at exactly precise places where the water moisture content has undergone some variations. So you need to know what the moisture content is at different locations. Maybe you can estimate these things with wireless. Okay? So it's a crazy world, and it's really fascinating to look at all these applications, sensing applications with wireless. Okay, chat. There are many messages in chat.
Does a human brain perceive electromagnetic waves?
Say that again.
Does a human brain perceive electromagnetic waves?
Oh,
that's with the brain.
Yeah, that's a question. Perceive as in understand?
Yeah, maybe.
Yeah, I don't know. I mean, it doesn't seem like, right? When there's a Wi-Fi signal coming to your laptop, it doesn't seem like we perceive anything. But
or maybe we do at a super micro level.
Super micro level, possible. I know of headsets that can pick up signals from the brain. I do not know what frequencies they are in. I used to know. I've forgotten now. Mohammed, there are definitely connections between RF signals sent out and the brain. The question is what frequency, and maybe Wi-Fi is at a too high frequency. The brain is not operating at that high frequency. But if you bring things down, I mean, there are products in the market where they are saying that I'll play certain kinds of music at certain kinds of frequencies, and that will be very good for your stress. It will relieve your stress. It'll bring you sleep. It'll do all kinds of things to the brain. And this is not a joke. This was one of the top products in CES, which is the Consumer Electronics Show that happens somewhere maybe in Barcelona or something. And they were the top product. So brain and RF signals and acoustic signals, a lot of stuff to talk about over there. So if you're interested in any of those, chat with me or start reading up. There's a lot of stuff happening. Other question. Oh, let me look at the chat quickly. I wonder if plants are that picky. Oh, plants are very picky. Plants are very picky. Maybe if the power is high enough, I'm sure you'd feel something. Maybe. Yeah, there are all kinds of discussions about too much radiation on the brain and on the body not being good. So, yeah. Okay, great. Where were we? We were here. Okay. So now that you can estimate RIR or CIR, and this is a function of the transmitter and receiver's location pair, this opens up two opportunities. What are the opportunities? One, you estimate the CIR H, the channel impulse response H, and use it as a more fine-grained fingerprint than just RSSI. You agree? Right? H is a vector. RSSI was one value per Wi-Fi access point. H is a vector that has all the information of the line of sight path, all the reflected path, their delays, and their amplitudes. So it has much more information. So it's a much finer grained fingerprint. So that's one opportunity. And the other opportunity you have from H is, why don't you estimate the first channel tap of CIR, and that should be the line of sight path power from transmitter to receiver. Are you totally on board? Is this totally clear? If I know H, I know the first value of H. The first value of H, as we talked over here, corresponds to line of sight path. If that's the line of sight path, I know the power. And if I know the power, I know the circle around Wi-Fi. But of course, things are not that clean in reality. In reality, this thing Y becomes H convolved with X plus this noise N. Right? As you go far away from the Wi-Fi access point, your signal becomes weaker, but the noise remains the same, because this noise is a function of the hardware. And not only that, can someone add some other noise here? Your neighbor, faraway neighbor maybe, is transmitting some other signal. That signal is coming and hitting you. And you have no way of measuring that signal. You do not know the preamble or anything of that neighbor. Right? So all of that makes your H estimate much harder. Right? So even if you do frequency domain Y equals HX plus N, H would become Y minus N divided by X, X preamble. Right? This would be your H. And then you do an IFFT on your H hat. This is in the frequency domain. And you would get H in the time domain. And this estimation has error from hardware noise and other. Let me move this a little bit. Other Wi-Fi APs. Is that clear? Very good. So, okay. But okay, this HT is still not that bad because, hey, this is a very high dimensional vector, right? Many echoes, and each H is a complex value because it has a delay and it has an amplitude. Right? Whenever it has a delay and amplitude, we think of e to the power j theta. Right? If that didn't make sense, don't worry about it, okay? So now suppose we fingerprint using this H. That is possible, right? Now I have this H and I now do the fingerprint. Instead of RSSI, I do it using H. But that still has a problem that it still needs labeled training data. You agree? Whatever we did with RSSI, where we went to each location, labeled that location with the location XYZ and orientation, that painful part, you still need to do that. Right? That's a problem. Also, environment changes will modify H. Clearly, echoes will change. So this is another problem. But you know, here's one more thing. Wi-Fi typically uses wide bandwidth signals, 20 megahertz. In your MP, you saw acoustic signals, which was 20 kilohertz. Wi-Fi uses 20 megahertz, right? 1,000 more frequencies in their signals. And Wi-Fi uses what is called OFDM, orthogonal frequency division multiplexing techniques. And you don't have to know any of these details. I'm just giving it to you so that as you encounter these keywords in your real world, don't get frazzled. These are not such a big deal. So what Wi-Fi does is, instead of sending a signal over all frequencies, it sends signals over small frequency bands. So this is what Wi-Fi does. It sends some bits on this frequency band, then on this frequency band, then on this frequency band, this frequency band, and all of them together give you 20 megahertz. And these individual frequency bands or narrow frequencies are called subcarriers. Okay. So this is subcarrier number 2. This is subcarrier number 128. So Wi-Fi basically divides the signal, the bits, in many frequency, narrow frequency bands called subcarriers, and there are 128 subcarriers. So what this means is, all I'm trying to say is, in reality, when you decode a signal with when you decode a channel with Wi-Fi, you actually get 128 channels for each frequency, for each subcarrier, right? Which means now you have H1, H2, H3, all the way till H128. So it's not that you're getting one channel, you're getting multiple channels, each for these different frequencies. And that has some value because now with 3 Wi-Fi access points, you basically have 128 times 3 dimensional space for your fingerprint. Does this make sense? With RSSI, radar, you had only one value per Wi-Fi access point. You had 3 values. That's why we drew that KNN in 3-dimensional space. But now you have 128 values for each channel. And with 3 Wi-Fi access points, you have 128 times 3-dimensional space for fingerprinting. More opportunity. This means it's more opportunity for accuracy or much better location resolution. Okay. So people have done this. There are results. Results look much better than RSSI, but the pain of going around that whole museum and picking up the channel estimates remains. And also as people move around, those channel estimates change. So definitely there are problems over there. But because it's a high dimensional space, the results look better. Okay? Finally, the last point is this is the first technique we talked about, which is this technique. Can you fingerprint based on the channel? But the other possibility is, why can't you pull out the first channel tap and use that as the line of sight power? That technique has one problem, which is the LOS power technique needs to know the transmit power. You agree? Right? If you need to know the distance, that distance, the distance is essentially P received. Remember, right? PR times K4 pi divided by PT, which is the transmit power, is equal to 1 by R square, or 1 by R square. Right? So to solve for R, you need to know the transmit power as well. And Wi-Fi APs can change transmit powers. You do not know. So that's a problem. And you need to know the AP location. And also, things are erroneous. If the Wi-Fi signal goes through a wall, hey, your range calculation completely gets derailed. Yes, John asked, can't transmit power be included in the signals in the preamble? It can be, but there in the Wi-Fi standard, there is no place where it can be. If you redesign the Wi-Fi standard, you can do that, right? It's possible, you're right. But the bigger problem is, if the signal passes this, let me write this over here. The bigger problem is LOS power erroneous due to walls and other obstacles. That is a major problem. And in Wi-Fi, there's so many signals that are going through walls. Even if you estimate line of sight power, it doesn't help you too much. Right? However, this painful training is not needed if you can estimate the line of sight power. And so there are trade-offs. There is no good solution. The problem still remains open. And I often tell people, if you can solve indoor localization, it's a huge deal. I think you can become a millionaire overnight. Okay. And also that enables a whole bunch of applications that were difficult otherwise. Okay. So this gives you the context, kind of wraps up what we wanted to talk about indoor Wi-Fi localization. And please ask me questions. If not, we are going to move on to a new form of localization around triangulation. But for that, we'll start off with some foundations in beamforming. Questions, guys?
For OFDM, does the channel estimated for each subcarrier or estimated as a whole bandwidth?
Channel estimated for each subcarrier.
Oh, okay.
Other questions? Take your time, no rush. Let me start. Yeah.
Considering the trade-offs for the two methods that you described, which one has been like more prominent in use lately?
Fingerprinting. So for instance, and we'll talk about this in another, after beamforming, when we talk about sensor fusion, we'll see that fingerprinting has probably gone a bit better. Part of the reason is that a company like Google is able to crowdsource the training data, right? Or Samsung or Google or Apple. A lot of people are moving around in airports, right? In shopping malls, and they have data from them. So if you get that training data and if you intelligently label them carefully, you actually might be able to get the training for free. You don't have to invest your own employees to actually go ahead and do that. And not only that, remember, Google has very nice Wi-Fi receivers on their Street View cars. You know, Street View cars go around the cities with their cameras, right? With their 360-degree cameras, right? So they also have Wi-Fi access points over there so that they're basically fingerprinting for outdoors, not indoors, but even outdoors, right? Without GPS, what do you do for localization? Especially in poor GPS environments where there are too much of bouncing around of GPS signals, they have fingerprinted all these streets quite well. So Google localization works better than GPS in many places because they're also using the Wi-Fi signals, and for that they've used fingerprinting. With line of sight power, I think the blockage issue is a showstopper, right? So unless you're in a place like a stadium or a park, right, where there are most line of sight signals, nothing is getting attenuated, there may be, but in general, I think it's a bigger hassle. It's a bigger showstopper. Deep, does that make sense?
Yeah, that does. And yeah, I think the idea you brought about that crowdsourcing, like that does make a difference.
Correct.
Because I was just thinking about it last lecture that it's sort of very unfeasible to kind of send surveyors and your own employees
right.
to every single shopping mall in the United States.
Exactly. But remember one thing, crowdsourcing is not easy. Why? Because you are not going to tell some random passenger in an airport, hey, can you label your current location? Right? That person who's moving around in an airport and gathering Wi-Fi data, even if Google has access to that data, Google doesn't know the ground truth location. Right? Whereas remember, in any of these fingerprinting techniques, you need to know the ground truth location. Right? So Google needs to do something more intelligent. And we'll talk about, in fact, some of the earlier works in research, where even from that unlabeled data, can you do something carefully to label them partially and use the labeled data again. So we'll talk about some of these algorithms where we iteratively label and use and label and use and so forth. Good stuff coming downstream. Any other questions? Okay, if none, we can start off with a new topic, which we call beamforming and angle of arrival. Very good. Okay, so let's start with, again, fundamentals. Guys, this course may not go into great depths of topics, but the hope that I really have is it gives you the certain building blocks, and that understanding that building block well doesn't make you a deep scientist, but it gives you courage to take on many other things that can easily build up on those building blocks. Okay, so that is why it's important to kind of understand these foundations well. Great. So omnidirectional antennas, as we talked about before, radiate signals equally in all directions, right? However, directional antennas direct the radiation more towards certain directions and less in others. Okay? So this is what an omnidirectional antenna would look like. On the other hand, a directional antenna would look like this. So signals are going more towards a particular okay, maybe not the last one. Signals are going more towards a particular direction and less towards other directions. You can think of this as an analogy. You can think of the omnidirectional antennas as a light bulb. You turn it on and energy goes in all directions. Directional antennas are like spotlights, right? It only focuses the light, or a flashlight which focuses the light in certain directions. So creating such non-circular radiation patterns is called beamforming. Okay. So the question we are going to look at today is, how do you form these beams? Okay. Now, right, in light, there's been a lot of work on forming these beams. And one idea that people have talked about from almost 1700s, I think, maybe late 1700s, 1800s, are lenses, right? You put a lens behind the light in a way so that the light reflects off the lens and they all add up at some place. In fact, the other day, I was watching a video on Fresnel's lens, on how these lenses, lighthouses in New Jersey and New York, they had these lights which was very poor. They would have these lights, and in fog and cloudy weather, the ships would not see these lights, and there's to be lots of accidents. Right? And then Fresnel came up and built this lens called Fresnel's lens, which actually was very nicely designed in a way that all the lights basically add up in certain directions, and they would make the light rotate, and the Fresnel's lens would be all around that light, and the ship would exactly see the light with much more power, and that saved hundreds of ships from kind of major accidents. Okay, so lenses. Projectors are another place where lenses are used. Someone said that in chat. Absolutely. So lenses have been used for light. Question is, what can we do with wireless antennas? And in wireless antennas, it's hard to do lenses. We want to do things electronically. Okay? We don't want to have mechanical structures around things. Okay? So the core idea is we want to consider Now, even in wireless systems, there have been antennas in which there are parabolas, right? I mean, you've seen these radars which are pointed towards the sky, maybe for extraterrestrial understanding or for different kind of deep space exploration. There are these huge radars that are these parabolic shapes, right? Balls, right? But we are more interested in electronic ways of doing it. Okay? So let's consider an array of omnidirectional antennas, or even microphones. So again, what we're going to talk about, beamforming, applies to RF, applies to microphones, acoustics as well. Okay? So here is a bunch of antennas, and this is often called a linear antenna array. And it often need not be always linear. There can be circular arrays as well. So for example, this is called a circular microphone array. And where have you seen this, guys? Circular microphone array?
Like Alexa or like design.
Alexa, exactly. So very much a circular microphone array. So these are essentially arrays, and one of the primary goals of these arrays is beamforming. I want to kind of focus my energy in certain directions, and the reverse. If someone talks to me from some direction, I want my ears to kind of tune onto that signal and separate and kind of remove other signals. So in some sense, you can think of beamforming as a filter, but it's a spatial filter, right? You're with me? It is a spatial filter, right? In space, you're filtering out things that are coming from other directions. Very good. So now let's say these antennas transmit all at the same time. Right? All these antennas are transmitting at the same time and transmitting the same signal, let's say a sine wave. The question we want to ask is, what signals will you receive at different locations if all these signals are transmitting at the same, all these antennas are transmitting at the same time? Look, all this while we were looking at a single antenna and we have some understanding of what to expect at different locations. But now we are saying we have an array of antennas all transmitting the same signal at the same time. What should you expect to get at different locations? Let's say L1. Okay. So consider nearby locations. Consider nearby locations first. Okay. Look, the aggregate signals at these nearby locations vary based on the location. If you are at L1, you are going to get some sine wave from this guy, some same sine wave from this guy, but at some other value, right? The two values are not going to be the same. Why? Let's say this is antenna 1. So let's say this is antenna 0, antenna 1, antenna 2, antenna 3. You're getting some sine wave from here. And you're getting the same sine wave from here. Do you think the values that you would get from antenna 0 and the antenna 1 would be the same? The value of that sine signal?
No, because they might be off in phase.
Yeah, why? That's right, Eric. But why? I want just one very simple answer. Why should they be off by phase?
Distance is different.
Exactly. Distance is different. Okay. Because the distance is different, each of these signals will have different values. They'll be off in their phase. So what you see over here and what you see over here and what you see over here will change dramatically. You cannot say much about what to expect at different locations. It's all going to depend on how the trigonometry works out. Okay. These kind of locations that are nearby is called near field. Okay. And we are not going to talk about near field because near field is much more complicated. And in most cases or most of the applications that we care about, we are actually pretty far away from the transmitting devices. Okay. So now let's consider locations that are far away. And we'll make clear what near and far means. Okay. So when distance from antennas to location L, and here is location L. Right? When distance from antennas to location L becomes much, much greater than separation between the antennas, let's call it separation D between the antennas, then do you agree that the signal path, so what we are saying is this D is the separation between antenna and this is the distance from the location to the center of the antenna array. If this D is much, much smaller than this distance from the transmitter to the receiver, let's give it a name. This is R. When D becomes much, much less than R, then do you agree that the signal paths from all the antennas almost become parallel? Do you agree with that? If Moon sends a signal to you from an antenna array, from Moon's Wi-Fi base station, the signals will all pretty much be parallel from each antenna. Right? Parallel lines meet at infinity. Right? So this is how we define far field when D is much, much less than R, so things are parallel. Okay? And now we will analyze let's analyze far field effects, meaning signals that are at the far field, what should they get when all these antennas are transmitting? Okay, today I want to stop because it's already 24. We want to stop in time at least one day. We will continue on beamforming, and I think next class would be interesting because I think it nicely shows you how beamforming can be effective, triangulation can be effective, and many of these ideas, so please do come to next class, many of these ideas will be very valuable in various wireless, acoustics, IoT, all kinds of things that you do in future, because these are foundational, and in many, many places you want signals to add up constructively. And these we will talk about techniques to do that. And we'll also talk about the reverse technique, meaning Alexa wants to listen to some guy who says, "Hi, Alexa." Alexa wants to kind of beamform towards that guy and only amplify that signal, and other TV and other people talking in the background or some microwave oven sounds, it wants to eliminate. So beamforming has this nice dual properties that I can transmit by putting all the energies in one direction, or receive by only receiving signals from one direction and suppressing all the others. So it has this dual transmit-receive reciprocity, and that's why I think it has many, many applications. Alexa is a great one. Wi-Fi access points is a great one. Triangulation, radar, self-driving cars, sonar, torpedoes, climate detection, right? You want to send signals towards clouds and understand those clouds for weather prediction. And you don't want signals that are reflecting from other places to pollute your understanding of clouds. So all these things have beamforming underlying it. So please come to next class. Okay, with that we'll end. And of course, I'll hang back, and if there are questions, I'm happy to answer, but we'll end the class today. Thanks, John, for the message on the chat.
Thank you.
Thanks. Question? Yes.
So far, I was just pondering over this. So for fingerprinting and labeling, I've noticed that like companies like Comcast and Time Warner have these Xfinity and Optimum Wi-Fi available in like malls and like a lot of public spaces.
True.
So they, since they have those there, they sort of know the exact locations of the access points.
Correct.
So
well, Deep, that might be arguable because localization is still not rolled out, right? So Comcast, AT&T, they're not giving localization. Okay, so the way they do it is they'll have contractors, and they'll tell the contractors, go and lay out these wires, put these Wi-Fi locations at roughly these locations, but they won't know the precise AP location. If they want to, they can go and figure out, right? Because they all own the Wi-Fi APs, right? Mm-hmm. But today, because they're not doing localization, I don't think they know the precise location of where the Wi-Fi AP is. Yeah, go on.
Got it. Yeah, so I think you answered my question. I was going around that track, that if they somehow get to know the precise locations, then they would be in a good spot to solve this localization problem.
But which technique would they use, do you think? Fingerprinting has that problem. which is how do you know what is the ground truth? Right? Suppose you walk around with a AT&T device or a Comcast device, and Comcast gets the RSSI values or even the channel values from your mobile phone, right?
Mm-hmm.
But it cannot train on that channel value because it doesn't know which location that channel came from.
Right. Yeah.
Right? You remember, right? In radar, Wi-Fi radar, we said that we need to know the guy who goes around the shopping mall collecting all the training data. That guy needs to know label the location where they are located. Let me try to get here.
Yeah.
Remember that, right? Yeah.
Right.
So where is my child? Wait. Yeah. Remember, right? We said that we need to know this location and this orientation when we are building up this training database. For crowdsourcing, you cannot ask the user walking around in a shopping mall, hey, what's your location? Right? So you do not have this information, which is the key problem. Right? So you have this data, Google, Comcast, they all have this data, where this data is the RSSI data from Google's own devices or Comcast devices or AT&T devices, what have you, right? But you don't have this. So you have to do something intelligent to label that data, because only after labeling can you do training, can you build up this map. Remember that, right? Because this map, every data point has a location L and an orientation theta, right? Without that ground truth, you cannot do KNN.
Yeah, I recently came across this one app that just asks you to turn on your location all the time, and based on how much you travel around or how much you commute, they convert those miles into some sort of like Starbucks credits, and they give you credits. So now I sort of understand why that location data is so valuable.
And also they would use GPS, I guess, to understand largely where you're traveling. Can they do something indoors? I think indoors it would be harder.
Right. Yeah.
Like they would more of use. So what are they saying? They are saying if you come into Starbucks over multiple times, we'll give you credits. Is that right?
No. So it's you just turn on the location in your phone, and depending on number of miles you travel,
I see,
they convert those miles into like Starbucks credits and give you. So they probably collect the GPS data and
collect the GPS data, right? Because number of miles you travel kind of makes me think that they are interested in the GPS data, not necessarily the indoor location.
Yeah, definitely a tricky problem to solve.
Yeah, it's a very tricky problem, and research community has been behind this for 10-15 years now, and been hard. And on top of this, someone's going to say, oh, I cannot do too much computation because that's going to drain my mobile phone's battery. So if you put all the constraints, it becomes a pretty tricky problem. I saw your email about the Kaggle challenge. I'll respond. But yeah, there's a number of competitions going on with localization. Yeah. Thanks.
Thank you.
Yep. Other questions?
I found this Neuralink description, and they are doing that already. Right. So instead of using wireless, they are just using PROS. Maybe in future they will be wireless.
That's right. I mean, Elon Musk is very much into this, and brain-computer interfaces are definitely a lot of work going on there. Totally.
Yeah.
Okay. Any other questions? If not, Thank you very much for coming today. And please ask your friends and everyone to come next class because I think it's an important class. Okay? I'll see you on Monday and get started with MP. Yeah.
Hey, Professor.
Yeah, Eric.
Yeah, so real quick, I think I emailed you about
I will respond to your email. I was really busy the last 3 days. I have your email in my mailbox. I'll respond to your email.
Okay, thank you. All right.